Let's continue now our discussion regarding this beam deflection topics. Right now we are going to discuss the first and fundamental method for solving beam deflection problems, and that's the integration method. As I have said in the previous videos, that there are actually a lot of methods available for solving beam deflections. However, due to time constraints, we can only consider two methods. The first one is the integration method, and later we will discuss the superposition methods. And by the end of this topic, you can see the advantages and disadvantages of the methods. Okay, so starting with this integration method. This method actually uses the fact that the second derivative of the deflection with respect to x, that's the distance along the length, is just equal to the moment function, so m all over ei. And take note that this m is we can write it as m of x. However, just to simplify the notations, then we can just write m. But just take note, this is m as a function of x, so meaning that it can be constants, or it can be linear, or it can be quadratic, or any other functions. Okay, that just means that the moment is changing along the x. Of course, that depends upon the loadings and the support conditions. Okay, this EI is what we call as the flexural rigidity. And if we have this differential equations, actually you can solve this using I think using separable or separation of variables. Okay, that method for solving this type of differential equations, that means that if we integrate this twice, okay, with respect to x, then we can actually obtain the general solution for the deflections. Okay, so if we integrate twice, what you get is a general solution. Okay, so that means it is an equation. Okay, when you say a general solution, it is an equation. But if we apply boundary conditions, okay, if we apply this, what we get is a particular solution. Okay, so that's the basic concept. But the question is, how do we obtain this moment functions? Okay, so this is the question. How do we obtain this? So we can obtain this by, so depending upon the problem, we can obtain it by cutting a section. Okay, cutting a section. Or if the given is the load, then we can actually integrate the load, or integration from the load, integration of the load function. Okay, so the idea is that if we have this load function, let's write this is omega. This is the load function. Now, recall that there is a relationship between the load and the shear, right? So right here, let's just write the shear, and then if there's also a relationship between the shear and the moment, okay, and if we integrate some more, what we get is, if we integrate after this moment, what we get is the slope, and then if we integrate the slope, what we get is the deflection. Okay, so here's our something like our key concept. Okay, so what that means, that the relationship with the relationship of the deflection from the load, or from the shear, or moment, is actually, we can obtain it by integration. Okay, so going down, we are going to do integration. Like For example, moment. So if we integrate the moment twice, okay, so what we can obtain is the deflection. Okay, and the opposite is that if we are given the deflection, then if we go backward, the operation that we need is the differentiation. Okay, so again, if you see this is the second derivative, so that means that if we take the derivative of deflection with respect to x, the first derivative would be the slope, and the second derivative would be the moment. So if we do it backwards, if we have the moment function, if we integrate it twice, okay, integrate it once you get this, integrate it twice you get this. Okay, so in terms of the graph, I have here this figure 10.6 from the textbook by Philpott. And if we have this beam loading conditions, simply supported beams plus a concentrated load at the midspan. Now we already learned how to draw the shear and moment diagrams, right? Now if you take the integral, then from the moment what you get is the slope. Okay, and if you take another integral, then what you get is the deflection. Okay, another one is, before we can solve, we need also to discuss these continuity conditions. This is something like the boundary conditions, but these conditions, says here, these are conditions along the beam span where the moment function changes due to the abrupt changes in the load and internal supports like internal hinge. Okay, so what it does is that it must, it says here that the slope and the deflection at the junction of the two adjacent segments must match. Okay, so right here, if we have an internal roller right here, so that means actually it's not, how do I say that, this is just a roller along the midspan. Instead of having, or let me try it here. So for example, we have this beam, and we have a continuous beam, and right here we have rollers, so something like that. So I am referring to this support along the midspan. Okay, so for that, the deflection at 1 is just equal to deflection at 2. However, they are just 0 because of this, because there is a support reactions here that doesn't allow deflections. However, for the slope, so you see here, this is the first segment, and then this is the second segment, and this is the junction right here. Okay, so what that means that the slope, they must match correctly. Okay, and therefore we can write the relationship of the slope of the segment 1 is just equal to the slope of the segment 2. Okay, so that's just what it says. And another one is for if there is a discontinuity in load functions. If you notice here, there is an increasing load, but right here at the segment 2, it's just a uniform load. Okay, so the continuity conditions just states that the deflection, okay, the deflection at 1 is just equal to the deflection at 2. Okay, and in terms of the slope, then it's just the same. Theta 1 is just equal to theta 2. Okay, and we also have this concentrated force and concentrated moments, and we also have internal hinge. Now for internal hinge, you would notice right here that the slope is 0. It just simply means that this internal hinge as we have always said that these internal hinge are something like it releases moment at this joint. So if you have moments in this segment, let's say if you have moments coming from segment number 2, it doesn't pass any moment to the segment number 1. Okay, so it's just like an internal release. That's why it is 0. Okay, so I guess that's enough, and we'll do our first sample problem. Oh, and by the way, let's discuss this procedure right here. Um, so these are the following steps for solving beam deflection problem using double integration method, and you see here that there is a term double integration, um, but for us here, let's just say these are just integration methods, because let's not just confuse this with other integration method like the direct methods. Anyway, it's just terminologies, and some other textbooks also just use integration methods. So first we need to sketch the beam. So that's the first step. Of course, at least we can have a visualization, or a preliminary visualization of the deflection, and then we need to solve for the support reactions, and then we need to select segments and make a cut and apply the equilibrium equation so that we can obtain the moment functions. Or if what's given is the load function, then we can also integrate from that. And then if we have that, then we substitute to the differential equations, and then integrate it twice. Then we apply the boundary conditions, then substitute all the constants, and then solve for the deflection at specific points when required. And another one last thing about this integration method is that there is a limitation for the use of this method, because it becomes lengthy when the moment function is more than 1. Like for example, here we have a cantilever beam. So you see here the moment functions, there is only one moment functions. And for this simply supported uniformly loaded beam, it's also one moment functions. But right here we have this as one function, and here is another function. Okay, so that becomes lengthy because of the mathematics, because of the arbitrary constants. Okay, so for the first sample problem, we have this taken from the textbook by Beer and Johnston et al. It says here a cantilever beam AB is of uniform cross-section and it carries a load P at its free end A. Determine the equation curve and the deflection and slope at A. So here's the beam situation. We have a fixed support here and a free end at A, and we have a load P. So there's no value, but of course if this is P, then in the mathematics we can just treat it as constants, of course. So we have this load P and the length L. Okay, so first is we need to sketch, right? Of course the sketch would look something like, if this is the beam and we have this load right here, then the deflection will look something like this, right? Okay, so next is we need to solve for the moment function, or calculate the moment function, or solve for the moment function. Okay, so how do we solve that? We can solve that by making a cut. Okay, so right here, let's make a cut. And here's our load P, right? And right here, there's gonna be, if we make a section cut, there's gonna be internal shear and internal moment, right? And of course, the distance from this section cut would be denoted as x. Okay, so this section cut, as you would notice, this will only produce one moment function. So at whatever x you cut, it will only have one moment functions. Okay, so now let's take summation of moment. Okay, and let's say we'll take summation of moment at x right here. So here's the value of x. Okay, so the summation of moment at x would be equal to 0. Okay, so from here, this P produces a counterclockwise, so that's gonna be negative P times the moment arm of x, right? Minus, also this one is counterclockwise, so this is minus M is equal to 0. Therefore, M is equal to negative P of not P of x, but rather P times x. Okay, so here's our moment function. So here's our moment function. Okay, then the next step is, okay, so apply the moment function to the differential equation. Okay. And we have EI times d squared times the second derivative of deflection with respect to x is equal to m. Okay, so recall that this EI from the denominator of this right hand side, I just transpose it here to the numerator of the left hand side. Okay, so here's our moment function, right? So we substitute the value of m, this negative P times x to this. Okay, so that means that EI times the second derivative of deflection is just equal to negative P times x. Okay, so here's now our differential equations, and therefore let's integrate both sides. And what the result of this would be, let's just write again, okay, but with integral sign, right, times dx. That means I'm taking the integral with respect to x, so negative P. So take note the P is constant, so I can just take that out from the integral sign. Negative P times x, of course, times dx, because the integral is with respect to x. Okay, so if we do the operation, what we get is EI times this one will reduce to the first derivative, dx is equal to negative P, right, times, this is just the power rule, x squared all over 2 plus the integration constant of c sub 1. Okay, so next is integrate again, because we need to integrate it twice, right? Integrate again. So what we get is, let us rewrite it. Okay, dx with respect to x, negative P x squared all over 2. Let's take the integral. Of course, we need to multiply this to dx plus c sub 1 dx, right? So that's gonna be our equation, and if we perform the integration, what we get is EI times the integral of the first derivative. What we get is just the deflection. It's equal to negative P. Okay, so x cubed right? X cubed, so 2 times 3, because the exponent, 2 times the exponent, that's gonna be 6 plus c sub 1 x plus c sub 2. Okay, so here's now our general solution. Okay, so in order to obtain the particular solution, we need to have we need to apply the boundary conditions. Okay, step 4 is apply the boundary conditions to solve for C1 and C2 for the arbitrary constants. Okay, so the first one is okay, what's the boundary conditions? So at let's start with this right here. Okay, so let's start with this at this or at point B. So we have, right, let's say this is our 0, and then this is our 0 line, and here's gonna be our x. Okay, so at x equal to L, what's the deflection? Okay, so at x is equal to L, the deflection is 0 because there is a support reactions, and therefore if we substitute this x is equal to L and deflection equal to 0 to this general solution, then what we get is 0 in this side. So this 0 is equal to negative p times L cube, right? Negative p L cube all over 6, okay, plus C1, okay, L plus C2. Okay, so let's use the second boundary conditions because we still have two unknowns right here. So at x is equal to 0, now let's find the boundary conditions at point A. So right here at x is equal to 0, then our deflection is equal to some values, right? So we have some values right here because it can go down. By the way, I guess this shouldn't be used because okay, let me redo this, right? Because if we have a free end, this is not a boundary conditions. It's right here from the text by Craig. Okay, so for free end, there's no actually boundary conditions, so it's not a boundary conditions for concentrated force. It's not also a boundary conditions or for concentrated couples. It's not there's no boundary conditions. So we can only consider the bounds of the moments at this supports. Okay, so let me redo this again. This one. So therefore, we only consider this. Okay, but since we have two arbitrary constants because we have C1 and C2, then where do we get our boundary conditions? So it should be because we only have to consider this fixed end, then the boundary conditions would be okay, the boundary conditions would be, okay, at point B, at this point, that's gonna be x is equal to L, right? If the distance is L, what's the deflection right here? At x is equal to L, the deflection is equal to 0, right? And we can also take the boundary conditions from the slope. Theta is also equal to 0 because this is a fixed support. Okay, so again, we will take our boundary conditions from this fixed and only, because right here there's no boundary conditions here. So at x equal to L, and this deflection is equal to 0, and the slope is equal to 0. Okay, so of course, if we use the deflection, just take note, if you use the deflection, then you have to substitute to deflection equation. Substitute to deflection equation, of course. Right here. Here it is. Here's our deflection equations. Right? That's the second derivative. But if we are going to use the slope, theta is equal to 0, then we need to substitute it to this equation. That's right here, slope equation. And this one is our deflection equation. Okay, so substituting now. Let's write it here. Substituting now, x is equal to L and theta is equal to 0 to the slope equation. Okay, so here's our slope equation. So this one will be 0 because the slope is 0, and this one will turn into L. Okay, so 0 is equal to, okay, minus p sub L squared all over 2 plus c sub 1. Okay, so therefore c sub 1 is just equal to p L squared all over 2. Okay, so that's our first arbitrary constant. Now the next is substitute. Okay, substitute x is equal to L, and we'll use the deflection is equal to 0 to the deflection equation. Okay, so here's our deflection equation. So this will be 0, and all the x will be translated into L. Okay, so this will be 0 is equal to negative p, right? Negative p times L, L cube all over 6 plus, what is c sub 1? Right, so we have the value of c sub 1 already. C sub 1 times L, okay, plus c sub 2. And since we have c sub 1, right, if we have c sub 1, then we can solve for c sub 2. And c sub 2 right here is equal to negative p L cube all over 3. Okay, the next is, okay, step 5 is substitute. Okay, substitute C1 and C2 to the deflection equation. Okay, so let's substitute. So we have EI times the deflection is equal to P all over, actually if you do the math, what you get is 6 all over EI times minus x cubed plus, okay, so let me do this in a shortcut way because of time. This is negative x cubed plus 3 L squared x minus 2 L cubed. Okay, so what we did is just to substitute the C2 and C1 to this equation. Okay, and then you do this, you simplify the equation, and what you get is this. Okay, so once you have this, this is now the particular solution for that given beam loadings and conditions. Okay, so now if we want to evaluate, okay, evaluating the deflection at point A, because we are asked to find the it's free and A. Determine the equation curve and the deflection and slope at A. Okay, so what is the deflection right here? Because we know this is the deflected curve, right? So we have a deflection right here, and we also have a slope. Okay, so let's find the deflection first, and that means that at the deflection right here would be at x is equal to 0. So that means at x is equal to 0, then the deflection is equal to p all over 6ei, right? So this 0 plus 0, right? 0 plus 0 minus 2l cubed, and therefore the deflection at A is equal to negative p l cubed all over 3ei. Right? That's the deflection at A. So if we have the value of p, the magnitude of p, and the length in the ei, then we can solve for the specific magnitude. Okay, then the next is evaluating the slope at point A, and of course we just have to determine the x value, which is just 0, and this will be from this equation. So we have the value of c1, right? And this is actually theta. That's the slope. So ei theta is equal to negative px squared, right, all over 2, okay, plus the value of c1 pl squared all over 2. And if you evaluate that at x equal to 0, then what you get is theta a is equal to pl squared all over 2 ei. Okay, so that's the solution. Right, now in the next video we will do another sample problem regarding this integration methods. Okay, by the way, just recall that for this free end we don't have there is no boundary conditions. Okay, so that's why we are only limited to find the two boundary conditions right here, and that's why we obtain boundary conditions from the deflection and the slope, because we have two arbitrary constants. Okay, so that's all. See you in the next video.